I don't understand this camera. Okay. What we're going to do today is basically a review. Of course, I can't review every topic and every operation, but y'all are real good with the operations, okay? If you got a system of equations, you can translate them into a matrix and reduce the matrix and do all that stuff. You can invert matrices, you can find eigenvalues, you can find eigenvectors. You can diagonalize a matrix, even if it's complex, I assume, since that assignment wasn't due until today, okay? But what I want you to do is have your work on the assignments, lay it out someplace so I can look at it. But I'm going to ask you to do a few things. And the first thing I'm going to ask you to do is list the things, the situations in which you would reduce a matrix. I want to see what you think. And I'm going to kind of go by the feel of you know, your answers to these questions to kind of figure out exactly where we're going to go with this review. So first question is, what are the various uses, the various contexts, the various situations in which you would need to reduce a matrix? Okay. Okay, so where and when would you reduce a matrix? Well, not sure how many of you listed the most recent stuff. You're going to reduce a matrix to determine eigenvalues, right? Eigenvectors. Okay, so maybe I'll put that in parentheses because really you just write out the equation. Okay. Well, if you reduce, yeah, if you have a repeated eigenvalue, say in three-dimensional space, you're going to get either one row of zeros or two rows of zeros. What's that tell you? Okay. So you might think about that. And I'm just going to throw that out because I don't have time to work through examples and make a bunch of mistakes, which I'll inevitably do. And since we're doing this, you know, kind of playing it by ear, which way to go through the material based on your responses, okay? But that's a situation you want to make sure you understand. Okay, how about doing a determinant? You reduce the matrix, keep track of your row operations, and you can figure out the determinant. Reduce the matrix to the identity, right? The homogeneous system that you solve to get the null space, okay? And the same basic matrix, except it's not, well, it's not a homogeneous system. You just reduce your matrix to get your row space because you're adding multiples of rows to each other and so forth. In other words, your row operations correspond to just adding multiples of vectors to others, and that doesn't affect linear independence. Okay, so that the rows that you end up with are linearly independent if and only if your original rows weren't linearly independent, and it's the corresponding rows. So if rows 1, 2, and 3 don't reduce to a row of zeros, then rows 1, 2, and 3 in your original matrix, or whatever rows you got by switching rows around from 1, 2, 3. Okay. In other words, the rows that correspond to the non-zero rows of your reduced matrix will constitute a basis for your row space, which incidentally then is the column space of the transpose. Okay, so that's kind of worth noting. Okay, and if you don't understand where that is, that's basically in the best developed in the section where you're doing the best fit stuff. I think it's section 5.4 or something like that. Okay. Okay, so in the process of determining your null space, determining your row space, you're going to reduce a matrix, right? Of course, the T comes before the E. Solve a system of simultaneous linear equations. Okay, there's another application. Okay, and these are applications you might not immediately think of, although that's probably one you will immediately think of. Okay, well, I'm not going to try to list them all, but as things pop up and some of the other questions I'm going to ask, you might add to this list. Okay, so I'm going to kind of leave this available. Okay, so let me just ask, any other favorites that you'd like to add? Okay, so added a couple of things. Somebody said, well, test for linear independence. That's pretty obvious, right? Okay. Then somebody said, well, find the rank. Of course, that comes from the same operation as doing the row space. So you want to see that connection. And also that gives you the dimension of the column space. And of course, nullity comes from the same process as finding your null space. Null is just the dimension of your null space. The rank is just the dimension of your row space. The number of non-zero rows that you get when you reduce the matrix to row operations. Starting to get choked up over the stuff again. Okay, now, so now, what about the 4 basic subspaces? Because this is a really kind of important picture of linear transformations. So to kind of jot down just a picture, a brief mention of what you know about the 4 basic subspaces so that I know what to say. Okay, so first place, you have the null space of your transformation. Okay. And if you're drawing the picture, you want to have the 0 vector over here. And the whole null space gets mapped to the 0 vector, which tells you what matrix you better reduce, what homogeneous system you have, okay? In other words, matrix times your arbitrary vector over here has to equal 0. So you're solving AX equals 0, right? So we could say you want to solve AX equals 0. Now, I've got a fairly small area up here to put a lot of information in, so I'm going to restrict myself a little bit, but I'll make some comments and you can look at the video and try to flesh this out, because of course, that's the way you really learn it anyway. So I might not be able to say I'll probably say a lot, but I'm not going to be able to write it all down. I might say a lot, assuming that there's a lot in my head at the moment. Okay, so anyhow, then your whole space maps over to the column space. The column space, of course, includes your zero vector. Okay, so the whole space maps into your column space. Now your column space has a basis that's the rows of the original matrix, because every row of your original matrix is going to appear over here. If you want the first row, you just multiply the matrix by the 1, 0, 0, 0, 0 vector, right? If you want the fifth row, if there are that many rows, you just multiply it by 0, 0, 0, 0, 1, 0, 0, 0. Okay? And we've seen that, so make sure you understand that, because that picture helps you understand what's going on here. You can memorize the, what the four basic subspaces are, but you want to try to understand them in terms of what happens to the matrix. So it's fairly obvious if you understand that why every row has to appear over here. Your column space is going to be spanned by the rows those are the two worst words I've ever written, the two most illegible words that have ever been written in the history of mathematics. So let me try to write them again. Combination of my incompetence and the fact that the chalk is sticking a little bit, but okay. I'm the right place for the chalk, and I can actually write. Spanned by, and let's be really specific. Just work being specific on. It's spanned by the transposed rows of A. And by transpose, I just mean every row of A becomes a column over here. And you just multiply the matrix by 1, 0, 0, 0, and you see that your row is going to become your column, right? So your rows are going to get transposed. They're going to become columns. And transpose of A's. They go here. And obviously the dimension will be the dimension spanned by the rows of A. Okay. And that dimension is going to be the rank, because the rows of A span the space of dimension equal to the rank. And of course, that is a dimension in column space. Okay. So that comes around full circle. So those are, and okay, so your column space and your null space both come from the matrix A that represents this transformation. Okay, well, I don't have much more room up here to label anything, but let's label now what happens if you apply the transpose matrix. Okay. So again, we've got V, it still has dimension M, and we got W. And W, of course, has a zero vector. And V has a zero vector. Okay, A transpose takes you from here to here. Okay, well, first place, some flash from the screen there, made me nervous. Okay, I'm a little paranoid, not sure what might be after me. The column space of the transpose is what? So in a manner similar to this, the transpose maps all of W into the column space of V. Okay. So now what's the column space of A transpose? Well, the columns of A transpose are the rows of A. Okay. So it's spanned by the transposed columns of A transpose. Okay. And gee, that's worth writing out. Yeah, I'll give myself a little room. Okay. Now, what are the transposed rows of A transpose? They're the columns of A. I think I did something wrong. Okay, so let's go back. A transpose. Consists of columns of A, right? So the rows of, I'm confused myself. Okay. So I'll let you alleviate the confusion. Okay. But it's fairly simple. If you get confused by this, as I just did, so I've got this, this is right, it's transposed rows of A transpose. I knew what that meant 30 seconds ago. And I can recover it if I need to, but it won't take time to do it. What's the dimension of the vectors in the column space here? Well, the dimension of V is M. So the dimensions of these vectors have to be M, right? Now the matrix is M by N, has M rows, N columns, right? So you come over here, the transpose matrix has N rows and M columns. Okay, so it has N rows. So when you multiply it by a vector here, you're going to get N components of your vector. Okay. So the transposed rows of A transpose are the rows of A. Okay. Think about that. See if I said it right. But that's going to be your row space of A. Now your row space of A is going to consist of the column space of A transpose, which makes a certain amount of sense. Think about the dimensions of the vectors, think about where they come from. Do an example. Let's do a 2 by 3 example, do a 3 by 2 example. Okay. And I would do that if I had time. Then you're, okay, so that's column space of A transpose is over here. Okay. So if you think about it now again, you have the null space here, and you have the column space of the transpose. They intersect at the 0 vector. Okay. That's the only place they intersect. Nothing in the column space is in the null space. Okay, because if you transpose something, or if you, this is the row space of A, and the row space of A doesn't go to zero, okay, except for the zero vector. So you want to consider that, okay? And then over here, you got the null space of A transpose. Now, I'm out of board space, and I'm going to leave it at that for the moment. But I want to get to the idea, the big idea here, of the direct sum. Okay, so over here, you've got P. You got your zero vector, and you have the null space. And you got the column space of A transpose, which is the rest of this. Okay. And it's not the null space of A transpose, it's the column space of A transpose. And by column space, to denote column space, a little confusing, and we talked about that. They use an R here, which makes you think of rank. Okay. So this is column space of A transpose, and this equals the complement of the null space of A. Now, I don't remember what symbol your book uses for complement. A lot of times complement is represented by a bar over the thing, but I don't want to use that because we just did complex matrices, and that would imply conjugate, complex conjugate, right? So we don't want to confuse that. So I'm going to use the prime, which kind of makes you think of derivative, but we're not doing derivatives of these things. So in this context, a prime means something different than it does in calculus, and Coach L immersed in calculus right now. Okay. So important ideas you want to understand. This means written badly now. Right. The intersection of these two sets consists of just the set consists, there's a set, these are sets. So the intersection is a set, and that set consists only of the zero vector. Okay. N of A is orthogonal to this, meaning, I don't have time to write it out. Every vector in the null space is orthogonal to every vector in R of A transpose. Okay. Now remember, R of A transpose just consists of rows of A. So any row of A is orthogonal to any vector that maps to 0. And we talked about that in some detail that month, 6 weeks ago. Okay. So you probably won't want to find that in the videos. You want to kind of read that. Okay. Now, this is an important idea. And you can think, actually, we did it more recently because we didn't do the linear regression until a few weeks ago. Okay. Pretty recent. Okay, what's this mean? What's this a symbol for? Anybody know the name of that? It's a big idea, okay? I'm not going to base a whole test on it. But there's a good chance there'll be something on this just to see how deeply you understand things, okay? It's a direct sum. And it's a fairly obvious idea. It just means that, first of all, these two have nothing in common except the 0 vector. Second, any vector in V is the sum of a vector in the null space and a vector in the column space of the transpose. Okay, this is closely related to why the whole regression model works. It's well worth thinking about those connections and then thinking about back to where would you want to reduce a matrix? Why would you want to reduce it? How does matrix reduction occur in the whole process of analyzing this stuff? Okay. Then, of course, over here in W, you again have I'm going to color code this. First of all, you have your 0 vector. And I'm going to use different colors here. I'm going to use blue. Okay. Again, you've got your null space of A transpose. And you have the column space of A, which is okay. The column space of A is just a set of all things that come from A, just like it goes over here, right? Okay. Null space of A transpose all converges into 0 vector. And we can make similar statements. I'm skipping some stuff here. Yeah. Try to fill it in. Don't spend days trying to figure this out when you need to figure out simple things. But if you get to the point where you figure this out, you really have pretty good command of one of the really important things in linear algebra. Okay? It'll stretch your mind a little bit. Yeah, we've done it. You've seen the explanations, but your web assigned problem assignments really challenge you on it. Okay? So I can say that this, that every vector in W is a sum of a vector in the null space of A transpose and null space. And the column space of A. So, for example, when doing regression, your target vector is going to be in the column space, okay? You want to project that onto the null space to find your best vector, because the null space, well, I don't want to just verbally make the whole statement because I might mess it up, okay, without writing it out. So I'm not going to do that. But think about how all this goes together to give you that regression line. It's kind of one of the capstone things in the course as we've designed it. Okay, well, I don't want to say any more about that, but those are your 4 basic subspaces, and that's a big deal. Okay. Now, your book does a nice job with the geometry of these things in a section that we didn't get to do, that I'd love to have done, but I'm filling in some of the blanks on applications of transformations, something like that, where you have shear transformations, family transformations, and so forth. Okay, first of all, eigenvectors. They okay, they expand or contract space in the direction of an eigenvector. They expand and I've got or here, I should say and. Okay, if the magnitude of lambda is greater than 0, that's absolute value is greater than 0, it expands. Absolute value is less than 0, it contracts. Absolute value happened to equal 0 because you can have 0 eigenvectors. It just means space doesn't expand or contract in the direction of that eigenvector. Consider the convergence of the population vector in the same dimensioned model. Because as your author very clearly states, you use your intuition in 2 and 3 dimensions to develop a geometric intuition about higher dimensions. You can't actually visualize them, and we've said it many times, use that insight. So if you have a 12-dimensional space, you can still think, okay, in the direction of this eigenvector, the space is stretched this way, and in the direction of this, it's inverted and compressed. Okay? Make sense? You want to have those pictures, and you want to think about lines in 2-dimensional space being subspaces. Okay? Your subspaces correspond to lines through the origin. We talked about it. Make sure you understand that. Okay? In 3 dimensions, your subspaces can be represented, your 2-dimensional subspaces would be represented by planes through the origin. And your 1-dimensional subspaces by lines in 3 dimensions through the origin, right? Okay, so you want to carry that insight with you, and you want to kind of think through everything in this course in terms of 2 and 3 dimensions, because then the only thing that changes when you get the higher dimensions is you just got bigger matrices and more equations. Okay? So you can't visualize it, but if you understand how it looks or feels in 2 and 3 dimensions, that's going to stick with you, with most people. Geometry sticks with most people a lot better than algebra and formal reasoning. It's kind of your basis for algebra and formal reasoning. Now, for some mathematicians, you know, they don't visualize all that well, but they're really good at symbols. So there are 2 kinds of mathematicians. Now, y'all aren't wanting to be mathematicians, you want to be engineers, but it applies to engineers too. How do you understand things? By the symbols, by the manipulations, or by the picture? Well, it's a combination of both. Which one motivates the other depends on how your brain's wired and also in your experience. So I think, again, our educational system is such that experience is more attuned to the symbolic than it is to the geometric, but we live in a geometric world, not a symbolic world. And I think for most people, the geometric intuition is more important. Okay? Then if you're one of those where the symbolic is more important, that's great. Okay? We need both. Okay? There's a place for everybody and every combination thereof. Okay, off the soapbox again. Okay, the geometric. Okay, now what everybody listed first, because of course you were just doing it with Hermitian unitary matrices and stuff, is diagonalization. It's worth writing if you have a full set. And the matrix consisting of those columns is your P matrix, okay? And it's worth noting that if your matrix is symmetric, meaning it's a real matrix, okay? It's equal to its transpose, okay? And I'm not going to write down that definition, but symmetric matrix is matrix equal to its transpose, okay? Then, if you have a full set of eigenvectors, if the eigenvectors are all distinct, then they're going to be mutually orthogonal. Now, St. Determinant model shows you that you don't have to have orthogonal eigenvectors, okay? Because your St. Determinant matrices are stochastic. They're almost always not symmetric, okay? And just think about it, you know, 0.9, 0.2, 0.1, 0.8, it's not symmetric, 0.2 here, 0.1 here, okay? So that's just one simple example. It shows you that non-symmetric matrices don't necessarily give you orthogonal eigenvalues, okay? They also have to have distinct eigenvalues to ensure that your eigenvectors are orthogonal. But if they aren't, if you have an eigenvector repeated so many times, you're still going to, you can still get a full set of eigenvectors. In other words, repeated 5 times, you get 5 eigenvectors if your matrix reduces properly, augmented matrix, okay? And you can think about what that means. And then you can Graham-Schmidt the things and make them orthogonal. And whatever they are, those 5 eigenvectors will all be orthogonal to anything that has a different eigenvalue, to any eigenvector for a different eigenvalue. Okay, well, that's kind of a big statement. You might want to replay that. Okay. And think about what it means. In any case, most of what you can expect from the final is going to be with a full set of with distinct eigenvalues. And I'm not going to give you a 12 by 12 matrix and ask you to find eigenvalues. It'll be two-dimensional, three-dimensional, okay? Because that kind of ensures that the thing is manageable, and there's still things I need to do to make them manage. Okay. Now, another thing I'll comment on, we haven't used a lot of software in this course, but of course, if you understand all this, then it's a very simple step. In an hour, you can learn how to use enough software to do a 12 by 12 matrix. You basically just do a 12 by 12 matrix. So, hey, what are the eigenvectors? And it tells you. Okay. Then you identify, are they distinct eigenvalues? Are they orthogonal? Well, you can do that. If you understand how to do it in 2 and 3 dimensions, you can figure out how to do it in any number of dimensions with good software. And it's not hard to use the software. I mean, yeah, there's a steep learning curve with some software, and a steep learning curve with linear algebra, but not at the level of what we're doing here, and not at the level of most undergraduate engineering. Okay. Now, if your mathematics is strong enough to get into the advanced engineering math courses and stuff, you get some really cool stuff. And I think y'all probably be candidates for that if that's where your interests lie. Okay, again, just a side comment. Okay. Anyhow, you understand the diagonalization process because you just did it for homework. So I'm not going to say too much more about it. But I think you understand the situation. And make sure you understand diagonalization with symmetric matrices and with Hermitian matrices, which are equal to their conjugate transpose, okay? So it's worth noting that symmetric Hermitian transpose conjugate, right? Also, okay, but tell me what you know about orthogonal matrices. We got time to give you 2-3 minutes on that. What can you tell me about orthogonal matrices? Why are they important? Give me a whole treatise, publishable. Give you 2 minutes. Okay, well, tell me what you know. Now, it's actually easier to understand orthogonal than it is unitary, and you should be basing your understanding of chapter 8 on your understanding of chapter 7, because chapter 8 is just chapter 7 with a little bit of introductory information on complex numbers and stuff. Okay? So you want to, your book does a nice job, at the end, I think of section 8.5, they've got a nice little table about orthogonal versus unitary, Hermitian versus symmetric. You see these analogies. So interestingly, people had trouble writing out most people, majority, had trouble writing out what an orthogonal matrix was, but everybody could tell me what a unitary was. Okay. So, well, okay, we can do that. We'll start with unitary. Now, not everybody got one. Okay, you either got the orthogonal or the unitary. If you get one, it's pretty easy to get the other. Okay, unitary means that A inverse equals conjugate transpose, or, of course, equivalently, if this is the inverse of A, then when you multiply it by A, you get the identity. Okay? Orthogonal means that, yeah, okay, if you want to write it out this way, or this way, okay? So there are just two sides of the same coin. And the only difference is you're really here talking about a transpose, but for reasons you want to try to understand, you have to do the conjugate transpose. Okay. Okay. In both cases, you get a full set of eigenvectors with real eigenvectors. Okay. Now, what does orthogonal mean? Well, if you multiply a matrix by its transpose, then if you do the first row by the first column, well, the first column is the same as the first row. You're just doing the dot product of the first row with the first row, right? And I don't have time to write all that out. I've still got, 13 minutes. But that doesn't leave me time to do other things. So I got to kind of wave my hands at that, but it's something that you should understand, okay? Again, first row times first column is just the first row dotted with the first row. First row times second column is first row dotted with the second row. Well, if A inverse A transpose equals the identity, that means that the first row dotted with the first row has to be 1, because that gives you the 1, 1 element. First row times the second row has to be 0, because that gives you the 1, 2 element, which in the identity matrix is 0, okay? It also means row 7 dotted, well, row 7 times column 7 gives you the 7, 7. It's on the diagonal, right? It's got to be 1 because it's the same vector, okay? But if you multiply row 7 by any other, you get the entry that's not on the diagonal, which is going to be 0, which means that that vector is orthogonal, because when the dot product is 0, when the dot product is 0, they're orthogonal, okay? Makes sense? So you see in the book where, just debating whether I have room, I'm going to write it kind of small down here. I wrote this wrong. I said A inverse times A transpose. Okay, A times A transpose, because A transpose is the inverse. I did it right here. Okay, and then I put the inverse there. Anyhow, A transpose equals I. If your rows are V1, V2, and so forth, okay, just the first two, the first little block matrix up here, the 2 by 2 block matrix in the upper left-hand corner, consists of V1 dot V1, row 1 times column 1, which is row 1 dotted with row 1. And that has to be 1. V1 dot V2 is row 1 dotted with column 2, which is row 1 dotted with row 1, essentially, right? Or row 2. And that's got to give you 0. So V1 dot V1 is 1, V1 dot V2. V1 dot V2 is 0. Okay? Meaning that V1 and V2 are orthogonal. V1 is parallel to itself. and has magnitude 1. Magnitude 1 because the magnitude of the dot product is, and the magnitude of the vector is the square root of the dot product, okay? And then similarly here, this shows you that V2 and V1 are orthogonal. Of course, you knew that from up here. And V2 dot V2 has magnitude, it is 1, so the V2 has magnitude 1. So everything's orthogonal. That's a really important picture, okay? Because orthogonal matrices are really, for reasons that I might get to and might not. I've got a whole list. I wrote out a list. I actually had some time yesterday. I got a project done. Had time to sit back and really think about what we need to talk about today, okay? So I got like 30 questions and I'm going to just kind of email you, okay? I don't mean that you should work through them. You should read them and see how many of them you think you could answer. And then kind of keep them in mind as you review. It'll help you. Ideally, it'll help you pull things together. If you got a better way to pull things together, that's fine. Okay. One of the questions is, what's so wonderful about orthogonal matrices? But with a little more detail to it. Okay. But one of the things that's wonderful is this. Man, this is pretty wonderful. Okay. Because, again, this, if your matrix of eigenvectors is orthogonal, then it really simplifies a lot of stuff. Okay, we need to talk a little bit more about that. But anyhow, unitary, well, there it is again. And metric implies that P inverse AP equals D, or P can be. It's not necessarily will be, because your eigenvectors might not all be of magnitude 1, but you can always divide them by their magnitudes to make them unit vectors. So P could be orthogonal, okay? Or can be, I should probably, could means maybe it could, maybe it couldn't, but it can be orthogonal. And region implies the same thing. P can be unitary. Okay, now y'all seem to have done fine on identifying unitary and orthogonal matrices and stuff like that, but that's why they're important. This is really why you do those preliminary exercises, so you can get to the exercises that have a little more substance, okay? And normally in this course, I like to do more proofs, but I decided to be reasonable and confine myself to web assignment. That's kind of to your advantage because I think it's worked out well for you, okay? I could have confused you with a lot of stuff. I confused you with enough. But, yeah, and again, ordinarily in a linear algebra class, we do a little more with proofs. I talk a little bit more about why things are. And I kind of like that because you go from why things are to formal proof. I think it's kind of easier to understand, for example, why an orthogonal matrix has the property I just described than to write it out as a formal proof. But once you understand it, then you can connect this to the formal proof, okay? A lot of times a textbook will give you the formal proof. Okay, I understand all those steps, but what's that mean? Of course, then usually, you know, your good textbooks are the ones that don't assume that you can fill in the details. And yeah, I mean, they're good textbooks that assume you can fill in the details. It's harder to read, okay? Then a good textbook like the one we're using, because I think it's an excellent textbook, will give you examples that show why the proof works. Okay, now my approach has been more like, here's what happens. Here's why it works. Now you read the proof. Okay. That might work for you, it might not. Just depends on how well you read, how well you imagine, and how sophisticated your mathematical understanding is, and also how your brain works. My brain works better by, okay, let's see, here's what it is, here's your pattern, okay. Now we can condense this into a nice, elegant proof that nobody can understand unless they understand why it works in the first place. Well, something like that. Okay. I don't have all the answers, and there are many mathematicians who understand things a lot more deeply than I do. Okay. Most people with doctorates understand things better than I do, but some schools give away cheap doctorates. None of them in Virginia. And not that many of them anywhere. It's kind of policed pretty well. Okay. And I'm talking about doctors in mathematics, not talking about mathematics education. Oh, yeah. A lot of them are very sharp too. Okay, go to close now. As I think I discussed, maybe off camera, but everybody's here, so I guess we don't really need this. I'm going to set up office hours, probably 11 to 2 Monday, Wednesday, and Tuesday and Wednesday during exam week. The exam will have to be done by Friday. I'll get you some sample problems by the weekend, okay? In the meantime, think about these relationships. I've got like 30 questions that I was going to print out for you today, and then I decided no, we'll just kind of play it by ear, see by feel what you can say, what you can do to answer these questions, and riff on them a little bit. Okay, I think maybe that worked out. Maybe it's an effective review, but we didn't review every detail, and of course you can't do that in an hour and a half. So kind of count my office hours being that. And if you got stuff you want to bring by, it's a really good time to do it while you're preparing for the exam. I think y'all are in good shape. Okay, I want you to be in even better shape. So I'll send you out my list of a bunch of questions like these. Might help you further sort things out. Use them if they work. If you got something that works better, it's up to you. Okay. So good luck. You've been a great class. It's one of the best classes I've had in years. Okay. You did your work. You came in prepared. You passed the quizzes. You showed me that you'd done stuff. Okay. Doesn't mean you never made mistakes, but there weren't that many of them. Okay. So that's how you learn. And I think y'all have a good future. Stick with it.